Well, then, hi everyone, welcome. Thanks for joining today's first webinar of NTech. My name is Denny, I'm a technical director at Nalis, and we're here to talk about Docker. We'll start today by an introduction of basic concepts, especially for those who are not familiar with it. Then we will focus on more practical examples and present more advanced possibilities. Before we start, just a few words about NTech. So NTech is a platform of technical events for several fields of expertise. It is designed to create a network of engineers around their passions. Today it's via webinar. Tomorrow, we hope really soon, it will be with physical events to create a much better sense of community and to be able to exchange more directly. All right, so let's start with the main topic of the day, Docker. To go more in detail about it, I'm going to leave it to Tim Gapens, a fellow engineer and embedded software specialist at Nalis. As I mentioned just earlier, for questions, we'll have a Q&A session at the end of the presentation. Okay, so Tim, the floor is all yours. I will mute
Okay.
and leave you alone.
Okay. Thanks.
See
Thanks,
you.
Denny. Thanks everyone for joining again. I'll share the presentation now, and then we can get right into the presentation. The presentation is built up in three sections. We'll start with the basic concept of what a container is. So just very general concept of what the container is. Docker is one of the technologies that we can use to enable containers in our production environment. So the second section will talk about exactly that, about Docker. This section is just meant to give everyone a quick introduction. So if you're new to Docker, this will be very quick introduction. So you just have a good idea of what is possible with Docker, but you'll definitely need more. And then afterwards, we'll go into some more advanced applications. So we'll show some advanced use cases in which we show some deeper aspects of Docker itself. So what is a container? Well, we can actually use a definition from the Docker website directly. So Docker defines a container as a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing environment to another. A container includes everything needed to run an application: code, runtime, system tools, system libraries, and settings. Containers share the machine's OS system kernel and therefore do not require an OS per application, driving higher server efficiencies and reducing server and licensing costs. So there's a few important parts here. The main thing is that a container is a bundle of everything that you need to run a certain application. It can be anything from a web server to a simple small tool, but it packages up all of the code and all of its dependencies. Um, on the other hand, the container does not need to contain any kernel modules, any kernel um, aspects, because those are shared with the host OS. So that's where the main difference is with a virtual machine again. It's a very useful comparison to make with virtual machines. Virtual machines run with their own guest operating system. So you typically have that hypervisor layer on which guest operating systems run, and then applications run on top of that. That means that virtual machines are typically a lot heavier, and that for containers, we can more see it like a containerized application. So each container represents more of a container. Each container represents more of an application that runs on top of the Docker layer, which directly uses the host operating system. So the benefits of a containers are then, of course, that it's more lightweight because it starts up faster because it doesn't need to go through a full operating system boot, for example. And we isolate at application layer. Sorry. That means that we have less overhead. The benefits of a VM are that there's a broader user base. It's more trusted in the industry because there's even more in isolation. We isolate at operating system level, so we have more isolation and we have more trust. But that also means that everything is heavier and it's harder to. There's more performance over it. So why don't we use both? Well, actually, both there is um, sorry, there's a few audio problems, I think, but I think that will get fixed. Why don't we use both? Well, actually, that's often the case on these big data centers. There's typically both of those running, where virtual machines will run on the hardware, and then inside those virtual machines, containers will be created to further isolate individual applications or individual clients' environments, for example. So, to summarize what a container is, a container contains all of the dependencies in a small and fast deployable unit. And the fact that it's so small and fast makes it easily disposable and very generic in the sense that it can be deployed on basically anyone's machine. So we have our basic idea of what a container is. Now we'll get into a quick introduction of Docker itself. So Docker is just one technology that we can use to deploy containers. There's plenty of other technologies, but we'll start with Docker here. Docker is composed of two main concepts. We have the images and containers. Images are your blueprint of what a container should look like. So an image contains all of the code, all of the dependencies, again, that is needed to run an application, while containers are a running instance of that image. So that means that containers are the thing that we talk about when something is actually executing our application that's running inside our container. The image is just the blueprint for that container. The containers are also what we talk about when we're talking about isolation, about reproducibility, and those containers are exactly what guarantees the if the it works on my machine problem. So we'll start with images. Images are typically composed of layers. So each image starts with a base layer, and then on top of that, we'll add multiple layers that add multiple files or that add remove files even. Just we layer them on top of each other. That means that in the end, our image contains all of our app code, all of the runtime dependencies, everything that your application needs to run. Again, we want to repeat that the container does not contain a kernel, no kernel modules. Those are reused from shared with the host. That means that there's also a very big variation, of course, between containers. Containers can be as small as one file, one executable file, for example, but they can be as big as a full Ubuntu image with all the system libraries that you typically associate it with it. Where do we get images? Well, there's three main options. We can get our images directly from the internet. The Docker Hub, for example, is a first-party provided store of images. So Docker provides the Docker Hub for everyone, generally accessible. Even we can upload some images to the Docker Hub with the right process, which means that that image will be available to anyone on the internet. Docker registry is a second option where we set up more of a private Docker registry that's typically used within a company, for example, but it can even be used for personal use, where you set up your private store of images on which you store, and it's a central point of distribution for your images. The Docker Hub is actually just a special version of a Docker registry. It's just the one that's accessible to everyone. The third option is to create images from scratch from Docker files, and we'll see later on how we do that exactly. So what is the Docker Hub? We want to go into that a bit more because that's the first thing you will get to touch when you start off with Docker. It's a central store for images, as I said, that anyone can use. Last month, however, Docker did put a rate limit on the Docker Hub. Actually, that means that now any unpaid or anonymous user has a rate limit on how many images they can pull from the Docker Hub. Generally, for personal use, that's fine. Like the rate limit is high enough. But if you're working in your company and you're pulling a lot of images from the Docker Hub, then you need to look into a way to limit that rate. So then we can get into our first Docker commands. The first Docker command that we're going to talk about is Docker pull, which we use to pull an image from a registry or from the Docker Hub in this example. We pull the Nginx image from Docker Hub, and we can use the colon, and then anything after that is the tag that we put on the image. So Nginx decides to put version numbers on their image, but the latest tag is typically used to indicate the latest version of that image or certain variants with the name Alpine here. Those are just ways to differentiate different versions of the same image. A few more commands. You can see that most of those commands have a long and a short version. Typically, of course, we use the short version when we're actually using them, but just to be complete here, we can pull images as we saw before. We can list all the images that are available on our local system. We can remove images from our local system just to free up space if we don't need it anymore. And we can use Docker inspect to show some more details on the image itself. We can then use those images finally to start up our first containers. So containers, as I talked about before, are running instances of those images. They're completely defined by the image and the options that you give when starting up the container. So those two completely define a container, and those are the ones that isolate the application, which have the application running in an isolated environment. When you remove a container, typically all of the changes that you made inside that container, everything that was done in that container is also removed. So we need some extra work to share data and to make data persistent if we want that to be the case, of course. So our first command that we can run to run a container is docker run. Again, a long and a short form, but typically we use a short form. Docker run with some options, the name of the image that we use, and then optionally a command that we run in that image, in that container, sorry. First example is a docker run -i. -i will make sure that we share the standard in with the container. -t will allocate a sudo tty to the container. Those two combined will just make sure that you have a proper shell into your container. You can properly interact with your container. --rm will make sure that the container is completely removed after we exit it, so we don't have any leftover containers hanging around on our system. --name will just name our container, of course. Ubuntu:/latest is the image that we're using here, and sh is just the program that will start inside our container. Another command that's useful with around containers is docker ps, again with the long form there, to show all of the running containers currently on our system. The -a option will not only show the running containers, but will also show all of the stopped containers on your system. Another option we have with containers is to run them in a detached state, which means that we'll just run them in the background. We do that with the -d option that you see here. And then we just start it up in the background, and we won't get any shell into it, for example. But we can still do something with it, of course, by Docker attaching to it. So we attach to it, and we'll get the shell as before. And we can then stop or start the container like we want with those commands. The final options that we have on Docker run are the -u and -v option. -u will simply set the user ID and the group ID that we have inside the container. The -v option can be used in two main ways. -v can be used to mount a host directory into the container. So in this example, we mount /home/me into the container at /tmp. That means that any data that's available on your system in home/me will be available on /tmp on your container. And any change that you make inside the container will also be written back onto your host. The second variant is by using Docker volumes. So my volume in this case is a volume that we created earlier with Docker itself. And volumes are typically used to share data between running containers. So we mount that volume into multiple containers, which means that all of them see the same information in that volume. It can also be used to keep some persistent storage when restarting some containers. If a volume is used, then we can keep that data persistent and just mount it every time. Okay, the final section of our quick introduction is about the Dockerfile. I mentioned before that we can create our own images. We don't need to pull them from a registry and from the Docker Hub. We can create our own images, and that's what we use Dockerfile for. A Dockerfile contains a set of instructions that each describe a layer. So I mentioned before that images are built up in layers, and every command will basically add a new layer to our Docker image. if so every instruction will add a new layer, and then you can basically use any layer as a full image, but of course we typically use the last layer as our full image. So how is it that brings us to the full flow that we typically use when using Docker. We write our first Docker file, and we use Docker build then to create a new Docker image. And then we can use that Docker image to spawn any amount of containers from it with Docker run. What will we write in that Docker file? Well, the most basic commands are just the commands that we use to add any type of files to the image. Typically, we start with a from command that will define our base image that we start from. That's something you pull from the Docker Hub, for example. This can be something as simple as from Ubuntu, to start from a normal Ubuntu install, or something like from Alpine, which is a smaller image that it's a lightweight OS, so it's typically used as the base of a lot of Docker files because it's smaller than a full Ubuntu, for example. Copy and add are both used to add files. Copy is a bit simpler in that it can just add individual files or folders. It can use wildcards, but it just adds simple files and folders to your image. Add will actually has a few more capabilities. It can actually use remote files from remote URLs, or even untar some tarballs if you have that on your system, and untar them into your container. Typically, if we don't need those operations, of course, we use copy to keep it simple, and then add we can use if we need those more advanced use cases. Run is used to finally run any command. Mostly that's used to install packages, of course, but it can be used to run any command on your container. Of course, we want the whole point of containers is to create a consistent environment. So there's some commands that we can use to set up that environment. Work there will change the working directory, of course. That will actually affect any subsequent command in the Docker file, and the last work directory that is set in a Docker file will set the default working directory when starting up a container that is based on your image. Env and user will finally set some environment variables and set the default user to be used in that image. The final commands that we want to talk about in the Docker file are command and entry point. Those will become very interesting later on, so I really want to mention them here. Command is used to set a default. You can use these two commands in two main configurations, basically. Command can be used on its own to set a default command. That means that if someone starts up a container based on our image and doesn't specify a command, it will run that command. So in this case, it will echo hello world for you. The other use case is to set both the entry point and the command, which means that we will set the executable that is always run when starting up a container based on our image, and we set some default arguments to it. Those default arguments can then be overwritten by the user on command line. That means that, for example, if someone runs a container that's based on our image with these two entry point and command commands, it will by default run git log on its in the container. And then if the user specifies a command after it, it will actually execute git and then whatever the user specified on command. We'll see later some very interesting use cases for that exact scenario. Finally, our final Docker commands are Docker build. Is Docker build to run Docker to build an image from our Docker file. So we use -t for tag to tag our image with a certain name, and then dot marks the directory in which our Docker file is located. Docker will build the image just fine, and then we can use Docker run test image, for example, to run our image with any of the options that we saw before. Okay, we'll then get into the demos. Those will show some more advanced slightly more advanced use cases. And they're also meant to give you a bit more insight into how Docker works internally. So we'll start with a very small tool called Dive. Just wanted to mention it here real quick because it's a very useful tool when designing your own images. Then we'll get into the Docker daemon Unix socket and what we can do with it. That will give us a good insight into how Docker works internally. Then the next section will give us a few tips basically on how to use containers to actually distribute our apps to our developers, for example, or to anyone who wishes to use our applications that we create. The final section is is on X11 forwarding, and it's just to show you a few more possibilities that Docker allows you to do uh, outside of the typical use cases that you think of. So we start with Dive. Dive is, as I mentioned, a very small tool written in Go. It's made to explore your image layer by layer. That means that we can very deeply inspect what every layer adds to our image, and that we can therefore have a very good view on what maybe redundant files are added to our image. The main goal of Dive is to help you in reducing image size, but of course, as a new Docker user, you can use it to have a good grasp on what is actually happening during your Docker image building. I've included a quick screenshot here. It's not too important what's on the screenshot itself, but I just want to give you an impression of what kind of information it is. So on the top left, we will see the different layers that your image is composed of. The currently selected one will give you some more details in the section below that. So we'll see the actual command that's running in there and a few hashes. The right pane will actually give us the most direct information of what is being added in that exact layer. So you can get a very good idea of which files are added, removed, and modified in that exact layer. You can filter, of course, with some filters at the bottom to filter on only added files, for example. And then finally, on the bottom left, we will see some more general statistics on the image itself. So we'll show you the largest files on your image, and it will try to see which files you don't really need on your image, and based on that, also give you an efficiency score. So that can be very useful in trying to reduce image size. Okay, just wanted to get that in very quickly. We'll get into the Docker socket now. So to get into the Docker daemon socket, we'll first have to explore how Docker works a bit more internally. So internally, Docker has at its core the Docker daemon running on your system. It's a service that when you install Docker and start up the Docker service, of course, it will always be running in the background on your system. And that's the tool that will actually manage all your images and containers on your system. Around that, we have the REST API that the Docker daemon provides, and that API provides a lot of endpoints for any operation that we want to do with our containers and our images. So any command that we saw before is actually a Docker CLI command. That's the final layer that wraps around it. It's a Docker command line interface. That's what we've been using in the introduction. And that one directly interacts with that REST API. So but basically anyone can write any tool that will interact with that same REST API, and you can write any tool to configure your own Docker containers and images. So as I mentioned, that Docker daemon API is by default is the listening point for your daemon, and it will by default be listening at the Unix socket at /var run docker.sock. But you can basically assign it to anything. You can even make it an HTTP socket if you want to control your Docker containers from a remote machine, for example. And most of the endpoints that the API provides are direct translations of your CLI commands that we saw before. So there's a few commands that we saw before that will contact multiple endpoints in the API, but mostly those, you can think of those as direct translations. So just to give you a good feel of how those endpoints look and to really get a good view of what we can do with those endpoints, I quickly wrote up a few curl commands that actually contact the Docker daemon directly. So you can see I highlighted the endpoint there at containers/create. So we can actually send direct JSON data to that endpoint, and it will create a new container for us based on a given image, for example. We can use containers/JSON to list the current containers on our system. We can then use the start endpoint to start up the container. And then finally, we can use the container/JSON command again to see that our container switched to the running state. Not that we would ever want to do this manually, of course, but I just wanted to go over that very quickly to give you an idea. How do we use that? How does that information become important? Well, this information is very important when we start thinking of alternatives to Docker and Docker. Docker and Docker is a very well known concept where we run Docker inside a Docker container. Typically, that was used for Docker development because, of course, it's very useful to create some experimental version of a tool you're developing, deploy it inside a container, test it, and then completely throw away that container and make sure that nothing, like, you can restart again and again on different experimental versions without too much hassle. So for Docker development, of course, people wanted to use that as well. So they wanted to run Docker inside their Docker container. That's why Docker also provides the D&D image that's set up to do exactly that. The problem with Docker and Docker is that in order to provide you the isolation that you expect, Docker needs some privileges on your machine. So that means that once Docker is running inside a container, that Docker instance inside Docker will also need those privileges. It means that we need flags like -- privileged, but there are also other security concerns that come with deploying Docker completely inside Docker. So it's not always the ideal use case. And most of the time, we don't actually need a full Docker in Docker. What most people actually need is just starting containers from inside Docker. An example of that is your typical CI/CD system. So typically, we have a daemon running on your host that manages some container in which something like a Jenkins is running, for example. Of course, we want to isolate our Jenkins instance, so we isolate it by running it inside a container. One of the jobs of that Jenkins may be to run some tests, some builds, for example. And of course, we want to run those in isolated environments as well. So we want our Jenkins to be able to start up containers itself. That's possible with Docker and Docker, but again, we don't really need that in this use case. We just need to be able to start up Docker containers from inside our container. How do we do this? Well, actually, what we can do is use the -v option that we saw before to mount a certain file from our host system into the container. In this case, we mount the Unix socket that is on our host system that is the endpoint on which the daemon is listening. That means that any Docker command that's executed in the manager will talk to that endpoint. And because of the mount, it will actually talk to the host daemon, to the Docker daemon running on your host. It means any command specified from that Docker CLI that's running inside your container will go directly to the daemon. And we can, for example, execute a Docker run command to start up a new container on the host directly, which means that the container is started as a sibling instead of a child. That's actually most of the time all we want with a configuration like this. And it doesn't require all the security concerns that I mentioned with Docker in Docker. So how do we do this practically? Well, I mentioned the -v option we use to mount the right socket into the container. And we can see that I'm using the Docker image, which is just an image that has Docker installed on it. We name it manager, and we run it in a detached state to start it in the background. And we can see with Docker PS that manager is indeed running. And then we can execute the next command, which is Docker exec. Docker exec will tell Docker to execute a certain command inside a container. So in this case, we Docker exec into manager, so our container that we just started, and we'll run the command on the second line, Docker run with the name runner. So it's just a very small example here. But that means that inside the container, we execute a Docker run command. And in the end, we will see that with Docker PS on our host again, we can see both of them running next to each other. That's exactly the scenario we wanted to achieve. Finally, we can execute Docker stop or any command from the host itself. So we can actually manage those containers directly from our host if we wish. Another tool that nicely shows how other third-party tools can actually use the daemon API is Pertainer. Pertainer is a very lightweight tool to manage your containers and images, but it takes more of a graphical user interface approach instead of the typical command line interface that you have with the Docker CLI. It itself is easily deployable as a container with the following command. Docker run, again, the important part here is again the -v. So we use the Portainer image that Portainer provides. We tell it to use this socket. And then finally, the -v option will actually make sure that we're talking to the host daemon directly. That shows how just any tool can basically interact with the Docker daemon to manage all your containers and your images. Just to give you an idea what Portainer then in the end gives you, I've included a few screenshots. You can have a nice list of your containers with some nice buttons up there to control them completely. Docker also gives you the ability to show individual resource usage on containers. So, of course, having a graphical user interface, we can make some nice graphs to visualize that, for example. Okay, our next section is dedicated to a few tips to distribute your apps in containers. Typically, when people start using Docker, they actually see containers more like a VM again. So they will see containers as a full OS in which you can jump into, execute a bunch of commands. If you start up the container, you can actually run any command in there. Typically, that's how people see containers when they just get started. Of course, we can go much further than that, and we can reduce our images to just really distributing our apps and just containing the binary and just its runtimes just our runtime that it needs. That's the end goal that we want to reach in this section. One tool that we can use for that is Docker Compose. So Docker Compose is actually a first-party tool that Docker provides directly for us. It's an orchestrator for our containers. So that means it's typically used in multi-container applications. You can imagine a scenario in which a web server is running, but it also needs some database application or some file server, whatever. And of course, we need those running. We want those running in containers, and we want to split them up in multiple containers. That's where Docker Compose can help us to start those up always in the same configuration and to make sure that they work together nicely. Another thing that Docker Compose can help us with is volume management. So we mentioned that briefly in the introduction, where we can create volumes, Docker volumes, to share data between different containers. This is what Docker Compose can also help us with. It can automatically create certain volumes that we want and mount them into the right containers to share exactly the data that we want. How does Docker Compose work? Well, actually, it's very simple. We just need one YAML configuration file that will specify all of the containers that we want to run, all of the volumes that are needed, for example. And then there's a few very simple service commands that we can just execute if we want to start up our application. We have a small example of a Docker Compose YAML file. This is just a single container application. It's called Droppy. Droppy is just a small HTTP file server that you can use on your Raspberry Pi, for example. So we specify our image that we want to use. We specify some environment variables. We specify which port we always want to mount when we start up this application. And we specify a few volumes that we want to mount. So this indicates that always when we start up this container, we want to mount the configuration and the data folder into our containers so that they're always available. You'll notice that these are basically the options that you would give on command line when executing a Docker run. But specifying them in here gives us a nice definition of our full application and reduces the need to share commands around to get your application running. Because in the end, with this Docker Compose file, our end result is very simple, and we can simply use Docker Compose up next to that Docker file, next to that Docker Compose file, and it will start everything up just as we want. Even if that's just one container right now, if it's multiple containers, it will start up all of those containers with this simple command. So of course, it's a very nice goal to reach. The next tip that we have is a very small tip, but very important one, where we get back to our entry point that we introduced in the introduction. I took a small example here with Askinema, which is a small tool. But the thing is that the tools that Askinema provide often need these large Node.js dependencies that we don't really want to worry about on our local system. So we want to use Docker. That's exactly what we want to use containers for. What Askinema does is set the entry point inside its Dockerfile to the executable that we always want to execute when running containers based on that image. That means that we don't need to worry about that anymore as our user and the as a user. And the only thing we need to worry about is the -v option here to share, of course, some inputs and outputs with our host machine. And we just need to start up a container. So all we need to do is specify the image that we want to use. The rest that's highlighted in black here, well, the part in black here, is the part that is just the arguments that we would give to the tool if it were installed on our local system. So like that, we more see the whole red highlighted part of the command here as the binary we execute, and the rest is just arguments that we pass directly to it. No more seeing it as a separate container in which we can go into and execute certain commands, but just seeing it as a runnable image, basically. The final thing that we want to, well, that is a good tip for when we want to distribute our apps, is to, of course, reduce our image size. The image, if we want to distribute it, will get downloaded a lot, will be shared around everywhere. So, of course, the smaller, the better. One thing that can help us with that is multi-stage builds. Multi-stage builds basically allow you to inside one Docker file completely start with a fresh layer. So halfway through the Docker file, we'll just start with a completely fresh layer. The only thing we can do is copy individual files and folders from our initial stage back to the next stage. That will greatly ease reducing image size, and it will greatly improve readability, as it will be very clear to anyone reading the Docker file which files are on your final image. Now, this is much clearer if you use an example, of course. We use a real-world example here in which we wanted to use Bazel, a build system tool developed by Google, and we wanted to create an image that had Bazel on it. But of course, we wanted a very specific non-release version of Bazel. So we wanted to build Bazel from source. So again, this is a real-world example, so it's not that important what's exactly in this Docker file. But you can see that we had to clone a repository, we had to install a bunch of tools to build Bazel itself. Even download some support libraries. So we download some zip files and unpack them. But we may not need everything that is in there, or we definitely don't need the zip files in the end. So you'll notice that if we wanted to clean that up, we would have to execute some extra remove commands. We would have to worry about all this cleanup. Well, with multi-stage builds, we can just continue the Docker file. So this is all in one Docker file. We can just restart with a new from command. We'll start from a new Ubuntu image, clean image, and we install just the tools that we need when we want to use our image, not when we want to create our image. The important part here is the copy -- from commands. Those are used to copy artifacts from our previous layer that we named build, and then copy those individual files or individual folders into our final image. So you can see that we only need the final executable that we produced, for example, and some extra folders that we downloaded before as zips. In the end, that clearly shows to anyone reading this Docker file what is in the final image, and we don't need to worry about cleaning up our image anymore ourselves. The numbers also give a good result. So any single stage, without worrying about removing any old artifacts, gives us an image of over 3 gigabytes. A single stage in which we did some work to remove the Git repository, for example, remove the zip files, just got us up down to just over 1 gigabyte. But just using multi-stage, the Docker file became a lot simpler again, and we reduced it to only half a gigabyte. So you can see that multi-stage offers a lot of advantages here. So combining all of those tips that we just used, I can show you an example of how the image can be used with Docker Compose and the right entry point being set in the container. And we can ask our developers, for example, to run a simple command like Docker Compose run Bazel, and then the run colon hello is what you would typically add to any Bazel command if you would be running natively on your host system. The thing is that the developer can just see the red part as the executable again and specify any command after it. And he doesn't need any dependencies installed on its system. The only dependencies he needs is Docker and Docker Compose. Everything will be downloaded. Everything will be right where it's supposed to be for your developer to run it. And that's, of course, the final goal we want to achieve with Docker. The final example I have for you is X11 Forwarding to show you a bit more of get out of that typical use case where, of course, Docker containers are typically used in a command line interface. But we can actually do more with that. We can actually do graphical things inside containers as well if you want. Now, X11 is the server that's typically running on any Unix-like system, and it provides your backbone for your windowing system. So it's the backbone for any graphical user interface that you have on your Unix-like machine. And of course, how do we communicate with that X11 server from our container? We use the X11 socket that it provides. So we apply the same logic as we used with the Docker daemon socket with the -v. We mount the X11 Unix socket from our host into our container. We set some extra environment variables and we share some extra files that X will need to properly connect to the socket. But in the end, we just share that socket. We start up our custom Firefox image, for example, that we created that just has Firefox installed in it. And running this command will start up a normal Firefox window as you expect before, except that it will be running inside a container. And that's, of course, very useful for graphical applications because, of course, those often bring these large dependency chains, and we want to maybe experiment with different browser versions, for example. And this can be a very usable scenario to test those out. Of course, this is a bit manual to run this always, so you have to worry about that kind of stuff. So there's actually a tool called X11 Docker that's basically just an open source wrapper around X11 and Docker itself. And it allows you to balance security and the kind of shareability that you need between your host and your container. Of course, interacting with X sometimes brings some security concerns with it. It really manages a lot of stuff on your system. You need to start worrying about stuff like keyboard logging. That's all stuff that X11 Docker allows you to configure. And it also allows you to add support for things like a GPU-driven application or share sound or webcams or whatever you can think of that X manages for you on your host system. So I have some final examples here. The first example that we run was XFCE. From the XFCE image, just run a terminal. You should know that this window that you see is not just a shell into a container, but it's actually the full window that's spawned that's running inside a container. So just the full terminal is running inside a container. We can finally show off the GPU stuff that X11 Docker can provide for us to render some gears, for example, that with our host GPU from inside a container. Okay, so with that, I think I talked about everything that I wanted to talk about. So we'll see if there's any questions now, and we'll be happy to answer them.
I get back in. Thanks, Tim. Thanks a lot
Okay.
for this very interesting talk about Docker. Yeah, we do have a few questions.
Okay.
Do you see them, Tim? Should I? Otherwise, I have them on screen. I can, or should
Yeah, I can
just.
actually see them.
You can see them. So the first question are from, well, the first few questions from Anonymous. Maybe the first one about the U option. So.
Right. So they're asking about the -u option to specify the user. The
Mhm.
1000:1000 is actually the user ID and the group ID. So the first part is the user ID on any Linux system, and then the second part is the group ID that you typically
Yeah.
specify. So it's not really Docker specific, but it's just a general way to specify the user on your system.
Yeah. There's another one, interesting one, about the need of the minus y, the dash y flag in the run command.
Yeah, so I think we're talking about an apt command here.
Yeah.
So the run command was used to run a certain apt command to install Git, if I remember correctly.
Yeah.
That the dash y is just to confirm apt to continue in case there's any questions. So typically, if you run apt on your system, it will ask you, okay, these are the things that I'm going to install. Do you really want to do that? And you have to type yes or whatever. The dash y will make sure that apt continues, because of course when we're building an image, we're not interacting with that process directly. There's no standard in when we build an image. It just needs to happen automatically, all of it. So that's why we specify dash y to auto confirm every step in that process.
All right. Another one again from anonymous. So what about then the use of the entry point and the override that we can do?
Okay, so indeed, I didn't mention that, but it's a good question. By default, you can actually override the command, as we said, by just specifying it with your Docker run command. The entry point by default, well, you can actually also override it with the dash dash entry point flag. So it's a more advanced flag, but you can run that Docker run with dash dash entry point to even override that entry point if you do want to override that. Of course, that's less common, because typically if we set entry point, that's really meant to, the container is really meant to be used with Git, for example, in the example we used. But dash dash entry point can be used to override it anyway.
All right. Well, again, another question from last one from anonymous. So how do you handle projects separated into different repositories? I can imagine indeed, client, server, repos, or I would say different applications which need to run together. So how do you do that with Docker Compose, and how do you solve this?
Well, yeah, that really depends on your exact use case, of course. I know that the Docker Compose part here that we mentioned was very brief. There's a lot more possible. There was like the most basic Docker Compose configuration file that we just wanted to fit in to give an example. There is a lot more possible with Docker Compose, sharing different folders, making the right volumes to get them all into the right location in your containers. There's a lot possible there, but I know we went over that pretty briefly. But yeah, that would require a whole new
But
session basically to get into that kind of configuration.
indeed, to summarize on this, I could say, well, it depends on the repo,
Yeah,
whether you have a monolithic repo or multiple repos. And of course, whether you can or not use a repo manager, something to store your Docker images. And you mentioned that you have the Docker Hub, you have
yeah,
also the possibility to set one up for yourself. That would also be useful. But to get more in detail, that's something else that
yeah, indeed.
would probably be best to answer in a separate session or something.
Mhm.
All right. Next up, Denise. So, well, she's asking a few questions. She wants to know again about the -h option in the Docker run command.
Yeah, I think that was in the where we started up the Portainer. That's actually a Portainer specific option. So that's just the option that we use to tell Portainer to use that location as the to talk to the daemon. So those just had to be aligned. Basically, the -h was telling Portainer
Mhm.
use this socket to contact the daemon API, and then the -v was forwarding that location from inside the container to the same location on the host. So the -h was a Pertainer specific option.
All right. And another interesting question about Docker Compose. So Anise again, she wants to know the difference between Docker Compose up and Docker Compose run. She
Right.
thinks that it
Yeah.
seems to be running in
I
the same folder, but there's a
yeah.
bit of a confusion. Maybe you can clarify.
I used both indeed, but I didn't really mention the difference indeed. So Docker Compose up you will run that next to your Docker Compose configuration file, and it will just start up every service that is in there. So that means that for our use case, that was just the droppy service, but it can be a lot of services and it will just start them all up for you. The Docker Compose run, sorry, was specified. Indeed, it seemed like I was specifying an image there, but what I was actually specifying was a service that's defined in our Docker Compose file. So I didn't show that Docker Compose configuration file because I didn't want to go over that
Mm,
again. But actually, there was in that Docker Compose, there was a specific service that was called Bazel. And with the Docker Compose run, we actually specified to just run that service
mm,
and to run that service with the command that we specified after it. So it's
yeah,
just a specific way to start at
yeah,
certain.
yeah. Yeah, the up starts, creates
Yeah.
containers and starts everything all together. And with run, you can specifically start one service and
Yep.
the collection of
Yep.
containers you want to
So
run.
that may have been a bit confusing with the image name and the service name there, but the service name is the Docker Compose concept, and the image name is the Docker concept. And Bazel was in this case the
Yeah.
service.
All right. Next up, Geert, here's a question about are there pre-requirements for third-party application you want to build an image for? I'm not quite sure if the question is clear to you, but
Yeah, I'm
yeah,
not entirely sure either.
yeah,
So I can say that building an image, you can see it as well as like building an image doesn't happen on your system. It happens inside the container already. So basically, image building is like executing inside a container. So you specify the from command to pull an Ubuntu base image, for example. Any command that you will run on top of that will add a new layer and will actually be running in that on that image, basically in a container that is based on that previous layer, basically. So any command that you will run in there doesn't require any pre-requirements, if that's what you're asking,
mhm.
because it's just running inside a container already. It doesn't interact with your host system, except if you start adding files directly from your host, of course.
Yeah, indeed,
So I
yeah,
don't
yeah,
know if that answered your question. I'm not entirely sure what you're asking otherwise,
yeah.
but yep.
If there's follow-up, I would ask here
Yeah.
to indeed ask another question, but I indeed besides Docker on your host, everything else that you do to create an image and so on is actually going to run yeah, within the base image that you're
Yeah.
referring to. So if you need something like curl, wget, or whatever, it's going to be specified in your Docker file, and then you're going to be able to use it from there. Okay, next questions. I'm looking at the time. We have still a few minutes.
Okay.
Question from Bart. Is it possible to map users from a Windows host to a container? A Windows
I
host, what is that?
that's actually it's a good question, but I don't have any personal experience actually. There's another question about using Docker on Windows systems. I don't really
Is
have any personal experience with
uh,
running
I
Docker on Windows,
I
so
I
I'm not completely familiar with the specifics of that. Maybe you have more
I
information
have
than me.
some knowledge. Well, we did not mention too much. Well, the whole thing about Docker is that it's designed and then it's using Linux kernel features to isolate and to
Mhm.
run all of this. So that's a bit too technical for this presentation, but yeah, it's using a number of features that are included in the kernel. For Windows and Mac users, you can use Docker. It's called Docker Desktop. What it does is actually that it creates a virtual machine, a Linux virtual machine, and you run Docker on top of this machine. So there are some shortcuts that the Docker Desktop is doing, but basically you are running a Linux image in there. The issue is, yeah, making this world cooperate. So between Mac and Linux, it's fine. You have users. You besides the IDs, the numbering, which is different. You can map stuff between those two systems. For Windows, it's however a bit more complicated. It is possible. According to my experience, it is messed up. Um, it gets better now with the I think it's now released the WSL2, so the Windows Subsystem Linux. That is something that actually improves greatly the virtual, so the Linux experience on Windows because it's well integrated. The Linux virtual machine that is created is well integrated into Windows system, so it more directly maps things together, but I didn't try out more
Yeah.
specifically about users. I know it's fixing up a number of things about performance,
Okay. So there's
not everything.
both in the chat and the QA there's a few
Yeah,
messages coming in
voilà.
confirming that it's released and it's a lot faster as well. So
Yeah, the speed is impressive. Well,
yeah.
I'm using Windows as a virtual machine on my Mac, and yeah, the well, it was okay before, but it's really super fast. It's still Windows, it's still the ecosystem that you can use there, but with the WSL2 is greatly improved. So yeah, I would think about the way that you would start your virtual machine and use Docker within your virtual machine on Windows to make it this completely transparent. That would be, to conclude this question, the best way to make it happen. Otherwise, if you do it with the Docker desktop, you would have these issues with mapping, because IDs and concepts are quite different on Windows anyway. So the mapping is not too great there. I hope it answers the question. Also, the one from Tinza. So can we use Docker on Windows system? Yeah, just answered right now. Another question. Yeah, few questions, few minutes. So Julien, in order to reduce the image size, should you split the package install in different steps in the Dockerfile?
Well, typically we bundle those into one run command. The thing with layers also is that we have to watch out with layers is that we need to worry about like rebuilding the image as well. So what happens is that when you build an image for the first time from a Docker file, of course it needs to build all of your layers. But then if you change a layer, it only rebuilds from that layer onwards. So we'll rebuild that layer and everything that follows. So you'll have to think about the organization of your layers in that sense, and it also brings with it the run commands. How many do you want to split up? It's a bit like depending on how often you change your Docker file as well. Um, but you can imagine that if you have this huge list of tools at the start of your image that you want to install, and every time you want one new tool to be installed, then it needs to rerun that full layer, and it needs to rerun everything that comes after it. So it all depends a bit on how often you change your Docker file and things like that. How often you want to change it, basically. So in that sense, that's the main motivation behind
Yeah.
bundling logical groups of commands, because you want to bundle stuff that if you change it, then everything in that layer needs to be changed anyway. So, yeah,
To add
it's
up
a bit of a balance.
just one comment there. Also be careful of the apt command. So yeah, you also want to see how to optimize, for example, using the no recommends flag to avoid install of additional
Yes.
packages that you don't need, typically documentation and stuff. They eat up a lot of space, and you typically
Mhm.
don't need those when running, well, for example, building stuff also. Just, it's time. Unfortunately, there is not much time to get on the question of Vincent saying that there is maybe an issue with running privileged
Yeah.
containers on a system. But
Just
just
very
to
briefly, that's actually
yeah
a valid concern,
yeah
because of course we are talking to the Docker, like the Docker daemon on your host directly. So you can add any option
yeah
um, on any option there to your Docker run command as well.
yeah
So yeah, it's a bit of a balance of finding where you put your trust, and you trust
mm,
your Jenkins system to start the right
yeah.
containers.
De-
It's
Definitely not the
finding your
best.
trusty locations.
Definitely not the best idea to deploy stuff and run it out there in the wild.
No.
Now, you can actually accept this risk when it's about building software and so on, I assume.
Yeah, definitely.
So time's up. Thanks for the presentation, Tim. Really interesting again. Thanks to all the participants and the questions that you asked. So that's concluding our first webinar.